Yeah, thank you, Katja, for the introduction and for the invitation also. Yeah, so I think I kept the title slightly vague. So let me try to say what I plan to do. If I can change slides. Oh, I should have tried this first. Ah, okay. Okay, I see. So I'm sorry. Um, so our main object is going to be the scattering map for Riemannian metrics, and I will explain in a second what exactly I mean by this. I mean, many of you will be familiar with it. I'm going to go over some basic definitions and some rigidity results, and then try to say something about the range. I can tell you right away, I can't actually classify the range, so that was sort of the hope. But I'll try to give you some ideas of in which directions one might explore structure in the range, and then how this leads quite naturally to considering certain biholomorphisms between twistor spaces, which I will explain how to get there. This is partially based on and sort of motivated by and motivating for some work I've done together with François Monat and Gabriel Paternine. So there's two papers that I'll try to cover some of the results of. So let's get started. What's the scattering relation I want to talk about? I'm considering surfaces. Yeah, so you can do all of what's on the slide also in higher dimensions, but I want to focus later on the surface case. So let's just stick with that. M is the surface with boundary, equipped with a metric G. And there's a bunch of natural objects. For example, SM, that's the unit tension bundle. So that's points and vectors, where the vector is length 1. That's a three-dimensional manifold. If M has a boundary, then SM has a boundary as well. It's a two-dimensional manifold. That's just those points and vectors where X lies on the boundary. And finally, inside there's a one-dimensional manifold that's called the glancing region. That's those vectors that are actually tangent to the boundary. So just two circles in this case. Yeah, so here's a picture of my manifold. You can think of it as a disk with some slightly perturbed metric. And on this manifold, or on DSM, yeah, so DSM is the boundary of SM. And so you should think of this as points on the boundary together with the vector that could either be pointing outside or inside. So this one is pointing outside, this one is pointing inside. And we define an equivalence relation on the set. We just say that two tuples xv and yw are equivalent if they lie on the same geodesic. Yeah, but this, I mean, they agree up to first order. So the geodesic actually hits y and it has the velocity w, and it starts at x and it has the velocity v here. And if this is the case, then I don't want to use this. This is just temporary notation. I just want to use this is my notation for the scattering map SG of xv. Yeah, that's called a scattering relation. It should be an equivalence relation. So if I have an outgoing vector yw, then I map this to xv again. Yeah, so I either flow forward or flow backward, and then if I apply SG to yw, I would get xv again. Okay, and if I look at the glancing region, so d naught of SM, so these are points and vectors that are tangent, then this would be the fixed points of my scattering map. Yeah? So S just sends these vectors to themselves. Okay, now of course S of xv is not always defined. There are several things that can go wrong. For example, I might start shooting a geodesic and it gets trapped inside, or it might sort of go to the boundary, but then immediately go inwards again and become tangent at the boundary. And I don't want that. Yeah, so like both lead to interesting problems, but they're very hard. I don't want to study this kind of behavior. So assume that we have a manifold that is non-trapping. So the first behavior is not allowed, and the boundary is strictly convex. So that means if a geodesic hits the boundary, it does so transversely. If I make these assumptions, then the scattering map as of xv is actually going to be defined on all of DSM. Yeah, so it can always make sense because I can always shoot in geodesics and they will eventually hit the boundary again. And there's a nice way to think about this geometrically. So in particular, these conditions imply that M has to be topologically a disk. But let's just assume this. So M is diffeomorphic to a disk. And DSM will be diffeomorphic to a torus, product of two circles. One circle just comes from parameterizing the boundary, and the other circle from rotating the velocity vector. So here's two cartoons of a torus. The same picture, you can pick whichever you like better. And so inside there, you have this one-dimensional manifold that's green on the left here. So that comes from going around the boundary tangentially in the correct orientation or in the wrong orientation. That's why there's two copies. And then the torus is split in these two halves. There's the blue half, which corresponds to the incoming vectors, and the yellow half that corresponds to the outgoing vectors. And so my scattering relation is defined on DSM. Yeah, so it's a diffeomorphism, actually. Yeah, so you can prove that this is going to be smooth. And it intertwines these two portions, blue and yellow. So whenever I take a point in the blue portion, that's an incoming vector, I can flow along my geodesic flow, wait until I exit again, and I record what I get. And that's some point on my torus again. Yeah. On the green portion here, which is the border here, it's just fixed points. Yeah, so I get a certain diffeomorphism of my torus that fixes these two circles and interchanges the yellow and the blue half. Okay. Now, first question we asked in this problem is, how much information does this map contain on the relevant geometry on G? That's of course a problem that's been studied quite a lot, and in 2 dimensions and for simple surfaces, there is a definite answer going back to Pestorff and Ullmann. That's now 20 years old. So they studied simple metrics. What does simplicity mean? It means that besides the 2 conditions that I showed you on the previous slide, namely non-trapping and strictly convex, you also assume that there's no conjugate points, which you can sort of think of as a unique geodesic between any 2 points. Simpleness is an open condition, so there's many examples of it. When you start with the flat Euclidean disk, that's simple, and whenever you perturb this a little bit, this will also stay simple. For simplicity, I also assume that the 2 metrics agree over the boundary. I don't really need this, then I would have to modify the statement, but let's just assume this, so that's quite a mild assumption. And what they prove is that like all the information on the isometry class of G is actually contained in the scattering. Yeah. So if the 2 scattering maps agree, yeah, so if the 2 torus diffeomorphisms are the same, then G1 actually has to be the same as G2 up to an diffeomorphism that fixes the boundary. Yeah, so the problem is natural gauge. You can never expect to recover the actual full metric tensor, but you only ever get sort of this isometry class up to isometries fixing the boundary. One of the directions is trivial. Yeah, going from the right to the left is easy, so the hard part is going from left to right. Now the conformal case, so by this I mean that if G2 is just a conformal multiple of G1, if I assume this additionally, then I only have to determine the conformal factor. That's quite classical, that's been known since the 70s, between Mukhometov. In fact, there was also a nice work, it was sort of 10 years ago and 10 years after the Pestorff-Ullmann theorem, where Wen showed that it's actually enough that only one of the metrics is simple. Simplicity of the other one follows a posteriori. And there's many related things. So for example, you can try to consider more general metrics and allow for some form of trapping. Kolagi-Amu and collaborators have worked a lot on that. Interestingly, if you go to the setting with trapping and you stay in 2 dimensions, then getting the conformal class has been done. So that's been done in this paper by Colin. By getting the conformal factor itself is open. So the analog of Mukhometov's result that was proved first in the simple case is still open in the trapping case. At least if you don't, assume more information like some analyticity or add additional data like lens data. And then very briefly only, like in dimension 3 and higher, if you assume simplicity and some foliation condition. So simplicity, I'm assuming to well, maybe I should have written this, but I can say it verbally. So in the simple setting, you get some additional information for free, namely the actual exit time, and that determines the boundary distance function, and vice versa. So the scattering rigidity problem, if you assume that all metrics are simple, is equivalent to the boundary distance problem. And so that was tackled in this paper by Stefanov, Uman, and Basi. So under their conditions, you also get a corresponding theorem in higher dimension. But I want to stick with 2 dimensions. Okay, so that's a rigidity question. And for simple surfaces, this is quite well understood now. So I want to ask another question, namely, can we say something about the range? To make a sensible question out of this, I constrain myself to metrics that are, well, first of all, simple. And second, I fix the boundary behavior. The reason I do this is just such that DSM is the same manifold for all metrics inside the space here. Yeah, because if I ensure that over the boundary, the lengths of all vectors are the same, no matter which metric I choose to measure them, then this DSM, this torus just stays the same as well. So if I do this, then I can make sense of this map that sends G to the scattering data as indeed such a map that goes from the space MS, simple metrics, to this group of diffeomorphisms on the torus. Okay, and now this is a wonderful question, but also a very hard question. What's the range of this? If I give you a diffeomorphism of the torus, how do you know whether it arises as some sort of scattering data? There's a bunch of obvious things it has to satisfy, and as I just we go through that and see where it leads us. So there's a bunch of necessary things, yeah, for a torus diffeomorphism that it has to satisfy if you even want to be able to write a scattering data. So the first thing just comes from the definition of the scattering map. If I flow forward and then apply the scattering map again, I have to flow backwards, so I end where I started. It has to be an involution. Yeah, fair enough. So I only consider torus diffeomorphisms that are involutions. The other condition is it fixes the glancing region. Yeah, so these 2 circles inside my torus, they have to be fixed. Okay, fair enough. If I want to be a scattering relation, then I should fix that. Let's keep going. There's a symmetry assumption. Namely, if I flip a vector and apply scattering, I get the same thing as first applying scattering and then flipping. That just comes from the reversibility of the geodesic flow and like the construction I told you earlier, that will either flow backwards or forward depending on whether we point outside or inside. Okay, now you can think, okay, what further conditions can you find on the scattering map? The next thing is very classical. If you haven't seen it, maybe don't sort of recognize it first, but that is like a well-known fact. Namely, S is actually a symplectomorphism for a certain symplectic structure. What is this? It's the most natural thing you can put on it. Yeah, so you take alpha, that's called the tautological one form. You have to do this with respect to a metric, and since we're over the boundary, I just picked the background metric G0 that I chose at the beginning. So that's a one form. If I take d alpha, it gives me 2 form. And this is actually the symplectic form. Yeah, so that means it's non-degenerate, which is the same thing as saying it's an area form, at least as long as I stay away from the glancing region. So that's my little footnote here. So in fact, it's sort of the Riemannian area times some function that vanishes precisely the glancing. And this function basically measures the angle of my vector with the boundary. So if you've seen that before. Okay, so it preserves this this kind of area. Now you would ask, okay, you have these 3 conditions. Is this enough? Maybe I already can say that I'm in the range then. But maybe the next condition already shows that things start to get a bit more non-trivial. There's, for example, also this condition that you might not have guessed from the start. Namely, some other integral has to vanish. Yeah, so you pull back this one from alpha by the scattering relation. And you integrate along sigma. What does sigma do? You fix a point on the boundary and just rotate a vector once around by 180 degrees. So what happens if you do this computation is you pick up like a derivative of your exit time, which is 0 on both ends. So what I'm writing down here is just the fundamental theorem of calculus. Okay, that's another condition that you have to satisfy if you want to be a scattering relation. Now, suppose I satisfy these 4 conditions, what can I say? Well, actually, you can say something already, and that's a theorem due to Murago and Ivanov that tell you that if you expand your setting a little bit and don't only consider Riemannian metrics, but also Finster metrics, then those 4 necessary conditions are also sufficient, at least as long as you stay, close enough to your background. Yeah, so let's go through the theorem. Suppose you have some torus diffeomorphism S that satisfies all these conditions, A, B, C, D, from the previous slide. And you make 2 further assumptions. So first, I only want to look at scattering maps that are the same near the glancing. Yeah, so there were these 2 little circles, and nearby I just do the same thing as my fixed background metric G naught. And secondly, I only look at small perturbations. Yeah, of course, if you want to answer the question in full, it would be great to have something for like arbitrary torus diffeomorphisms, but it's a great place to start just with something that's close to some background. If you assume that, then you can actually realize S as the scattering map, not of a Riemannian metric, but of a Finsler metric. So let's quickly go through, okay, and this Finsler metric also agrees with the Riemannian metric near the boundary. So what's a Finsler metric? Finsler metric just means that in every tangent space of your surface, instead of giving yourself an inner product, you give yourself a certain norm together with some regularity conditions. So phi is a continuous map on the tangent bundle that's smooth away from the 0 section, and positive away from the 0 section. There's also a homogeneity condition, which you need to get a norm. And if you look at these balls, yeah, so all vectors that satisfy phi of this vector less equal 1, then this is a strictly convex set. Yeah. If you do this for a Riemannian metric, you get an ellipse. Here we allow like arbitrarily smooth, strictly convex sets, essentially. The result is more general, actually. So I only wrote down 1 version of it. You can also consider non-reversible Finsler metrics, then the symmetry assumption from the previous slide disappears. And you can actually do the same thing in higher dimension as well. Then this last condition also falls away. So that's quite a satisfying answer in some way for Finsler metrics, but of course the world of Finsler metrics is much, much larger than Riemannian metrics. Yeah, if I allow arbitrarily convex sets in the tangent space rather than just ellipses, I really have enlarged my space enormously. And it's completely unclear whether to tell how, in which case I can actually choose phi to be Riemannian metric. Yeah? So they construct me some Finsler metric, but it's not unclear whether I can tell in some way from the boundary whether this Finsler metric, which is not unique, first of all, there's no rigidity in this case, whether it comes from a Riemannian metric or not. So if you want to understand the range for Riemannian metric, you still have to keep looking further. Are there questions so far, actually? Feel free to interrupt me. Okay. Then let's continue. And now let's try something completely different. So this is an idea we had at some point about how to go about the range, how to classify the range. I can tell you right away, it doesn't quite work, but let me just lead you along the way and see how far we get. So we start with an observation that's as old, I guess, as the scattering rigidity problem was also used, I think, in the first sort of approaches to get rigidity. Namely, whenever you have 2 metrics, G1, G2. So I assume that they're in the set MS. So if you remember, MS contained all simple metrics that have a fixed boundary behavior, which I did to ensure that DSM, this torus, was the same for all metrics. Then I can always find the diffeomorphism of SM, so of my unit tension bundle, that intertwines the geodesic flows. There might be time change involved, but fair enough. And how do I get there? That's very easy. It's explained in the picture, basically. If you have XV that lies in SM of G1, so that's a point and a velocity for the first metric, then I can flow back along the geodesic of G1 until I hit the boundary. And then I flow forward with G2. And how far do I flow forward? Well, until I've reached sort of the same proportion of the full geodesic as I started with. So if I was like 75% along the way for red, I also go 75% along the way for green. That gives me a map. And well, I can make sure I have to modify a little bit to get something smooth. But fair enough, then I get this diffeomorphism. And by construction, it intertwines geodesic flows. Yeah, so it sends geodesics of G1 to geodesics of G2. And as a simple consequence, we get a second item. Yeah, if I intertwine geodesics, I also intertwine scattering relations. Yeah, so if I restrict phi to DSM, to the boundary of SM, let's call it psi, then I get this relation between scattering relations. Yeah. So there's two pieces of information in this observation. The first is like any two metrics are related by such it's called orbit equivalence. And whenever I have an orbit equivalence, then it intertwines the scattering relations. Okay, why do we care? Well, here's an idea. You know, instead of classifying the torus diffeomorphisms directly, maybe you could just say how to modify your background metric to go to a given one. Yeah, so if you look at this expression here, what the observation tells us is that any scattering relation of a Riemannian metric can be written in this way if I allow psi to be an arbitrary diffeomorphism for torus. Yeah, so if you can think of this like every scattering relation lies in the conjugacy class of SG0 under this action by diffeomorphisms of the torus. Now, if I allow all kind of diffeomorphisms, I get a huge space. I get much more. I get, again, all Finster metrics, and I get things that are not simple. And so if I just say, I look at all of these things, I get too much. Now, I could wonder whether I can restrict the class of diffeomorphisms such that the torus diffeomorphisms that are carved out by restricting the set of psi's corresponds exactly to the range. Why would I hope that something that works? Well, it has worked before. That's sort of the main motivation, I would say. So you know, there's a few inverse problems where we understand something about the range. The geodesic X-ray transform for simple metrics is one of them. It goes back to a paper by Pestov and Ullmann also. The Calderon problem for conformal structures in 2 dimensions is one of them. It goes back to Shalafutinov. And there's also one for the nonlinear X-ray, which is a nonlinear version of the geodesic X-ray transform that I did together with Gabriel Patanay. In all of these cases, actually, the crux to characterize the range was something exactly akin to this idea here. Yeah. So first describing the range in terms of some sort of orbit structure. You had some group action, and you say, well, the range is characterized as everything that lies in the orbit of a fixed anchor, of some fixed background thing. Yeah. Well, here's my fixed background thing, and I sweep through with my group action. Can I, you know, restrict now the group elements such that I get exactly the range? So, you know, after we understood the nonlinear X-ray transform, I was quite excited, and I thought, well, maybe that's also an approach to go, you know, about the scattering relation. Now, the next question is, how do you find H? How should you, what's a sensible way of restricting psi? You know, that you get like a new question, why should this be easier? Well, in all of these problems, you found a corresponding restriction by looking for holomorphic things in some way. Yeah, in all of these cases, it was important to respect the complex structure of what? Well, I think it's easiest for the Calderon problem for conformal structures. So there, in the range, you look at Dirichlet-Neumann maps of metrics on a 2-dimensional manifold. And what Sharafutinov proved was that any 2 of them are related by a diffeomorphism over the boundary. Where does this diffeomorphism come from? Well, from the Riemann mapping theorem. Whenever I have 2 conformal structures on the disk, then there is a diffeomorphism that relates the conformal structures. That's the Riemann mapping theorem. And that's exactly where you get your conjugacies over the boundary from. For the X-ray transforms, linear and nonlinear, we also use some form of complex geometry, but then it lived on twistor space. So let me tell you what I mean by twistor space and what one could reasonably conjecture would be the correct space here. So that's what I've been trying to say. There is sort of a natural way to make sense of looking at psi's that are holomorphic. What is this natural way? Well, you look at twistor space. What is that? I define this like another manifold, ZG. That's something I can do, by the way, for any like Riemannian surface. Should be oriented. What is it? And now I fill in all the disks. Yeah, so SM had a circle living over every point. Now I have a disk living over every point. That's a four-dimensional manifold. And I can put a complex structure in this. Like if I say it like that, it's boring. It's obviously a subset of the tangent bundle that comes with a natural complex structure. But I don't want to use that one. I want to use a different one. Namely, I can use one that's tailored to the geodesic flow and that complexifies the geodesic flow in a certain sense. That's a transport twistor space. Let me go through an example and then say a few more words about it. So what's the Euclidean case? We look at M being R2 with the Euclidean metric. And then Z is the unit disk bundle. Yeah, so if I use complex coordinates, then I have one coordinate called Z, one coordinate called mu, and I look at disks, so I only want mu to be an absolute value less equal than 1. Okay. There's many ways to describe a complex structure. One of them is by saying which functions are holomorphic. So I tell you what it means for a smooth function to be holomorphic. Namely, it means to satisfy some Cauchy-Riemann equation. Now, if I delete this red term here, I just get two Cauchy-Riemann equations. I get just the standard one in Z and the standard one in mu. So that would be like the boring complex structure. But I do something different. Namely, I add this term here such that the two variables interact. And what happens now if I go to the boundary, yeah, so to the area where mu has norm 1, so then I'm on SR2, on the unit tangent bundle, is I pick up again the geodesic flow. One way to see this is that the restriction of F to SR2 satisfies two conditions corresponding to the two Cauchy-Riemann equations. One, its fiber is holomorphic. That comes from the second condition here. And being on a circle, you can, determine this by just looking at the Fourier modes. There shouldn't be any negative Fourier modes, and then you can extend it to the disk in a holomorphic fashion. And the first Cauchy-Riemann equation tells you that F has to be a first integral. So first integral means it's constant along the geodesic flow. So that just comes from this operator here degenerating, and degenerates in such a way that you just get back your transport equation. So twistor spaces in various forms have been around for quite a long time. It goes back to work of Penrose. This particular one is more related to something that's been considered by Hitchens and Lebrun and Mason. And in the context of inverse problems, Gabriel and I started sort of looking at that. And there's actually a nice talk also by Gabriel in the Irvine inverse problem seminar that you can have a look at, where he gives some more details on that. And it's a very nice construction to think about several objects that naturally occur if you study geometric inverse problems in 2 dimensions. Suddenly they become sort of natural objects from a complex geometric point of view. So here I want to do something similar. So I want to look at holomorphic torus diffeomorphisms. But what do I mean by this? Well, I could, for 2 metrics, G1 and G2, I could try to find a biholomorphism between the 2 twistor spaces, and then only look at those torus, only at those psi's, so the things that conjugated my scattering relations, that arise from such a biholomorphism. So that will be a guess for this H. And the guess it simply comes from like the heuristics I had on the previous slide. I want to look at things that somehow respect the complex structure and the twistor structure. Okay. Now, Z is a real four-dimensional thing, meaning it's a complex two-dimensional thing. And so this very much smells like a sort of Riemann mapping theorem, like we used for the Calderon inverse problem, which Sharafutinov used. So now the question is, can there be some sort of Riemann mapping theorem for transport twistor spaces? So that's a question I think we had for quite a while. Now you look for evidence. How is the situation if you go from complex dimension 1 to complex dimension 2? Sort of the first thing you find out is, like, very classically, Riemann mapping theorem goes terribly wrong in general if you go to a higher complex dimension. Like, this is the classical example. If you take a ball in C2, then this is not biholomorphic to the product of two disks. Yeah, this is, I don't know, probably over 100 years old, I don't know. Of course, both sets are simply connected. Yeah, so to find out whether things are biholomorphic, there's more things to check. It's more difficult. It's actually rather difficult in higher dimension. I'm not sure whether there's a very satisfying answer in general, actually. But there's also hope. So here's a theorem that gives you some hope. So this is, there's several versions of theorems like that. I'm quoting here one by Epstein or Young. That tells you something about Stein manifolds. And it tells you something about small, compactly supported perturbations. In that case, you have a Riemann mapping theorem. So if you start with X, which is a Stein manifold, I'll explain a bit later what I mean by this. But for example, this and that, they're both Stein manifolds. Yeah. If I start with a Stein manifold, and I take my complex structure and I wiggle it a little bit. Yeah, so it should be a little bit, so it should be close enough. In this case, it's enough to do this in like C0 topology, with also more general result, but that's not important to us. And I make sure that I do this within a compact set. Yeah, so I do my perturbation in such a way that I'm compactly supported. Then, in fact, the new complex manifold is going to be biholomorphic to the old complex manifold. And this biholomorphism I can also arrange to have compact support, basically. That's the identity away from this compact set that I wielded. So you think, well, there are some cases where you have a sort of Riemann mapping theorem, and these cases are related to Stein manifolds. So Stein manifolds are like a subclass of complex manifolds. One definition would be that they have to have like an embedding as a proper submanifold in some Cn. Okay, you can think of them as manifolds that have many holomorphic functions. Yeah, so anything that's a compact complex manifold is not going to be Stein for that reason, for example. And we sort of came to think of the twistor space of a simple surface as something that looks a bit like Stein. So while studying transport twistor space, we found several results that are very much reminiscent of what you can typically do for Stein manifolds. Yeah, so for some time we had sort of this idea around, well, simpleness somehow behaves like Steinness in the complex world. So maybe there is hope. Yeah, so if transport twistor spaces are a bit like Stein manifolds in a simple case, maybe I do have a Riemann mapping theorem. So that's what I tried for some time. We tried for some time. And then we ended up proving exactly the opposite. So that was quite an interesting turn of events. Namely, instead of flexibility, like the Riemann mapping theorem. So Riemann mapping theorem means you can deform your surface and still you get the same thing up to biholomorphism. Instead of flexibility, you have rigidity. Namely, whenever you take two simple metrics, then your twistor spaces are biholomorphic if and only if the two metrics are isometric. So that means there is absolutely no hope for anything like a Riemann mapping theorem in the context of transport twistor spaces. You can say a bit more. You can also say something about maps themselves. Namely, whenever you have a biholomorphism between transport twistor spaces, then this has to be a lift of an isometry. Yeah, so you have a little phi, there would be an isometry between G1 and G2. And phi is sort of the natural thing it does on the tangent bundle and thus on twistor space up to sine. Yeah, so this is the a typical map that is always going to be a biholomorphism. And we have an analogous result for another surfaces as well. That and in fact was a bit easier to prove even than the simple case, because we could rely on this recent paper by Colin, Thibault, and Gabriel on the Mach length spectrum rigidity for another surfaces. In the simple case, you have to do a little bit more. And then you wonder, is this a general phenomenon? Or maybe are they never biholomorphic? So like, the question is like, do you need simpleness or another to get some rigidity phenomenon like this? And we found like an exotic map that tells you that at least the second part of the theorem can't hold true in general. Yeah, so in general, there might be biholomorphisms that are not of this form. And here's one, yeah, and it's defined on the twistor space of R2, but it respects sort of translations, so you can also send it down to the two torus. So then you have the transport twistor space of a two-dimensional manifold and a biholomorphism that takes this form here. Looks a bit funny, but you can check that it's biholomorphism. And whenever this coefficient A here is non-zero, it's not lived. Yeah, so that's why I call it exotic. It's not of this form. Yeah, so that tells you there's really something to prove. Like you have to find some conditions where you do have rigidity, as in the theorem. How do we prove this? Well, it's based on the same techniques really as scattering rigidity or boundary rigidity, at least for the first part, to show that they're isometric. And then for the second part, to show that biholomorphisms actually have this precise form, we also need some form of identity principle that I can talk about later if there's some time.
Is this biholomorphism an open condition on the metrics? So if you perturb G1 slightly to get G2, are the twistor spaces going to be biholomorphic?
No. By the theorem, they're not. Yeah, so even if G1 and G2 are very close together, unless they're isometric to each other, the twistor spaces will not be biholomorphic.
Oh, okay, yeah, that makes sense.
Yeah, so but the theorem says more. It says like even if they're very far away, unless they're isometric, the twistor spaces will not be biholomorphic.
Okay.
Yeah. So that tells you in particular that there's no analog of this theorem here. So this theorem told you that if you do small perturbations in your respect, like everything outside of a compact Z, then there is a biholomorphism. But this is not true here. Even if you only perturb G1 inside of a compact Z away from the boundary, then you're still not going to get something that's biholomorphic.
Okay, yeah, interesting.
Okay, so I want to just use one slide to talk a little bit about the proof and compare it a bit with some other forms of rigidity. So let me now formally introduce a word that I've used before, namely that of orbit equivalences. So whenever I have two metrics, G1, G2, I again assume they're in the set MS. So recall, these are simple metrics that agree to a fixed background on the boundary. Then whenever I have a diffeomorphism between the unit tension bundles that intertwines the geodesic flows, so it sends geodesics of G1 to geodesics of G2, that might mess up the time parameterization, but it sends the geodesic to the geodesic, then we call this an orbit equivalence. And you've seen the picture before. Yeah, so we had this observation previously that I recall here again as a lemma. They always exist. Yeah, there's many of them, in fact. So I could always, like instead of returning at the boundary here, I could flow out a little bit until I hit some other set and then flow forward, and then I get a different kind of diffeomorphism that will have the same property. So whenever I have two simple metrics, there's in fact many orbit equivalences. Now, having the same scattering relations is exactly the same thing as having an orbit equivalence that fixes the boundary. So if you look at this construction again, where you flow backwards and then flow forwards again, we always guarantee basically that this is the identity at incoming vectors, just by construction. So if it happens now that the green line would actually end up at the same point in the same direction as the red line, that would be the same thing as saying that the orbit equivalence is actually the identity everywhere on DSM, then that's exactly the same thing as saying that S1 is the same thing as S2. And now you can see sort of what biholomorphism rigidity buys you, or what biholomorphism should say, what they buy you. Whenever you have a biholomorphism, so of course, I was not terribly precise. I put a complex structure on Z1 and Z2. Now you might complain Z1, Z2 has a boundary, and in fact, this complex structure is also a bit funny. It sort of degenerates at one of the boundary components. But let's just say it's biholomorphism of the interiors. Then everything is well defined. I have like honest to God complex surfaces. And I just assume that they're smooth up to the boundary. So that makes sense now. Then I guess the first question I can ask myself is, like, can I understand what a biholomorphism really is? I mean, I can write down a definition. It has to be, of course, a holomorphic map in charts if you want, or you can write it down in many other ways. But can I make sense of this in some more useful way that's more adapted to how we think about, say, orbit equivalences? And yes, you can. So whenever you have a biholomorphism and you restrict it to the unit tension bundle, which is like a portion of the twistor space, then you get an orbit equivalence. That basically comes again from one of the Cauchy-Riemann equations that respects the transport equation or the geodesic flow. So it's not so surprising that also on this nonlinear level here for biholomorphisms, that's what you pick up. Yeah, so phi, the restriction of the big phi, is an orbit equivalence. And there's a second condition that is again reminiscent of fiber-wise holomorphicity. And you can, if you want, call it fiber-wise holomorphicity again. Namely, if I fix a point on the base, then I get a function that just depends on a disk, my vertical disk, and this has to be holomorphic into my second twistor space. So there's two conditions, and this is again equivalence. So if you want, you can think of biholomorphism rigidity as saying that, to get rigidity in this context, having this boundary condition, phi equal to the identity at the boundary, is as good as this holomorphicity condition. Yeah, so it's a form of rigidity where you don't put this boundary condition, but instead you have a rigidity condition on your orbit equivalences. Okay, so I think I'm coming to close already. So here's sort of the things I want to get across in the take-home messages. So if you want, you can think of biholomorphism rigidity as a rigidity phenomenon along a list of a lot of other problems that we're interested in inverse problems, and hence also some sort of inverse problem, if you want. It fits naturally next to scattering rigidity, conjugacy rigidity, or Mark length spectrum rigidity. Yeah, so instead of these boundary conditions on the orbit equivalences, we have these holomorphicity conditions. And again, we show some form of rigidity. The second thing is the question that I started with. Can we say something about the range of this map? And the answer is, well, it's still mysterious. That's why I gave the caveat already on the first slide. I said, too disappointed. There was one guess that we had, which was to sort of find this sort of holomorphic orbit structure, which is the thing that worked for several other inverse problems. So, like for example, the nonlinear X-ray and for the Calderon problem in 2 dimensions. At least this guess here doesn't work. Yeah, biholomorphism rigidity tells you there's no way you can make this work. And then lastly, there's sort of a broader point to sort of motivate studying these twistor spaces. So I think there's just a lot of really interesting interactions between inverse problems on the one side and transport twistor spaces on the other side. And like many inverse problems just generate interesting questions about them, like that are of complex geometric nature. So here's some examples. So that's the identity principle that I mentioned earlier, and that we use to prove also the biholomorphism rigidity theorem. So whenever you have 2 biholomorphisms so I fix one twistor space now. So there's only one metric involved now. And I take 2 automorphisms, meaning they go from Z into itself again. And they're holomorphic. If they agree on SM, do they agree everywhere? Now, this sounds extremely natural, as you might agree. That's typically the behavior we expect from holomorphic maps. but we have this degenerate SM. So this is actually like a rather non-trivial question. And we solved it using results from inverse problems. Yeah? So we used this studying the normal operators of the geodesic exponents form. So that's one of the papers I cited at the start. So that's one nice example where you see that the theory you develop for inverse problems also buys you technology to understand these twistor spaces and prove complex geometric results. There's more questions. I showed you that on a torus, if I take the twistor space of a torus, I get these exotic automorphisms. And I showed you that on the Anosov case and the simple case, we have rigidity. Other than that, we don't really understand what's going on. So it would be very interesting to get some form of biholomorphism rigidity outside of the simple or Anosov setting. Want to produce more counterexamples beyond the torus. And of course, you can try to go the other way around. You can try to seek out complex geometric tools to try and prove something about inverse problems. I mean, that's sort of one of the questions I think that's been in the background of looking at these twistor spaces. And they've been very useful, I think, to think about many structures, but we haven't really used them as a tool yet. So that's certainly an interesting question. And then finally, there's another question I think that has been around sort of a couple of years now that we don't understand very well, namely actually the question when Z is Stein. So we know it in some cases. For example, whenever you start with the disk or you start any domain in the plane, then the corresponding twistor space is going to have a Stein interior. But maybe that's not even the correct thing. Maybe you rather want to sort of find the notion of Z up to the boundary being Stein. Yeah, sort of classical notion of Stein manifolds is for open manifolds, and Z has a boundary. So you should maybe think about what this means. There's all questions that you come to think about, sort of starting from those problems if you want. And that's in fact all I want to say. So thank you very much.
Thank you very much, Jan, for the very nice talk. Thank you so much. Are there any questions or comments, please?
This might be a very basic question, but so if little phi that intertwines the geodesic flow, it is the restriction of a biholomorphic map of the twistor space if and only if the manifolds are boundary rigid. Do I understand this correctly?
So this third point I make here, no, that's true in general. That doesn't have anything to do with rigidity.
But you said this big phi, the existence of such a biholomorphic map only exists if the two manifolds are boundary rigid. Isn't that the theorem you guys proved on the previous slide?
Exactly. But now suppose I take any G1 and then any G2. They don't have to be simple. They're just arbitrary metrics. And then I can ask you, what is a biholomorphism? Yeah, so a biholomorphism has to be a diffeomorphism that's holomorphic. So what I'm doing here is just I'm writing down holomorphicity in a different way. And then this is how it looks like. So that's just like neither 2 nor 3 are deep. There's no rigidity in here. This is just sort of a rephrasing in both cases. And sort of the rigidity question comes afterwards. Suppose S1 is the same thing as S2, and you get this phi, can you then prove that they are isometric? Or in 3, suppose you have a biholomorphism, and hence you have like this package of information, can you then prove you have an isometry? And then this rigidity question, which is a lot harder, we understand in the simple Nosov case, but not in general.
Okay, I see. Thank you.
Thank you very much. Any other questions or comments, please?
I have a question.
Please.
Okay, so why don't you study the boundary distance function instead? And it's a generating function of the scattering relation in the first place, so you don't have to worry about this symplectic structure.
Well, it's a question what you think is easier. I mean, like the Burago-Ivanov paper, they have 2 theorems. One is about the boundary distance function, one is about the scattering relation. And you're right, in some sense, the theorem for boundary distance function seems easier. I think like one reason I like the scattering relation is also because you have a group and you have sort of like more structure if you want that you can work with and just instead of just a distance function. But But I mean, I haven't found a nice range characterization, so who knows whether this is a good way to pursue. But somehow it seemed like having like this diffeomorphism group in the background gives you a bit more to work with.
Yeah, I'm not saying that I know how to solve the problem through the boundary distance function. Just
Again?
I'm not saying that I know how to solve the problem.
Yeah.
Boundary distance function set of scattering relation. Just
Yeah.
that it's probably the result, whatever it is, it will sound simpler because you don't have to worry about the symplectic structure at least.
Say again, then you have which?
You don't have to worry about the symplectic structure. It's already implied because it is.
Well, I think that's a bit the question, whether it's a worry or whether you say that, working with this nice diffeomorphism group gives you actually more structure and hence sort of more things to try and understand the range. But I mean,
Okay.
Maybe that's not the right thing to do. It could be.
Okay, thank you.
Thank you very much. Are there any other questions or comments, please? Any other questions or comments, please? Okay, if not, thank you very much, Jan, for the very nice talk. Thank you very much, everyone, for coming. Thank you.